Yeah, ladies and gentlemen, it's a great pleasure for me to welcome you again on this Wednesday afternoon at our webinar about the dawn of the hydrogen economy, recent developments and activities. Slowly but surely, we are moving throughout the overall provision chain from hydrogen, where we started basically about with the, let's say, goals, what we are following this, and then we go surely, but step by step from the, let's say, production side to the transportation, and we will slowly moving forward to go further to the area of the use. And let's say today we will have two, from my point of view, very interesting and very, let's say, outstanding presentations. On one hand side about the interchangeability of hydrogen injection in pipeline grids from Professor Maher Ben Chib. He's from the National Engineering School in Monastir in Tunisia. And then we will have a presentation from about advances in hydrogen liquefaction from Professor Dr. Alexander Alexev. He's from Technische Universität München, so Munich University of Technology, as well as Linde, also in Munich. So we will have two very interesting presentations. So with this, I would like more or less to, let's say, make the introduction this time very short, not to talk too much from my side, and to pass over to my colleagues. Before that, I just would like to mention that, let's say, this webinar is organized by, let's say, and sponsored by GIZ in Tunisia. It's supported by the Green Hydrogen Society in Tunisia, and as well as the university in Carthago. On the other hand side, on the German side, we have, let's say, of course, Hamburg University of Technology. It's the VDI in Hamburg, and it's the Energieforschungsverbund also here in Hamburg. And as you might know, we have a simultaneous translation from English to French. So you also can listen to French. And with this, we made a short mistake. Sorry for that the link has been not the right one. But if you click on the old link, you will find there in the chat, let's say, a link where you can go to the new one. With this, I would like to finalize my introduction. And now it's my great pleasure, my great honor to introduce Professor Maher Ben Chib. Sorry, I'm still not perfect in this way, so please apologize for that. And he will give us an introduction about interchangeability of hydrogen injection in gas pipelines. So, Professor Ben Chib, the floor is yours, and we are very much interested in your presentation. Just go ahead. Thank you.
Thank you, Professor Martin. It's okay for my screen?
Yeah, very good.
Okay. So at the beginning, I would like to thank Professor Martin Kalschmidt and all the organizers of this series of webinar for this opportunity. I would like to introduce myself to this nice audience. My name is Maher Ben Chib. I am professor at the Energy Department of the National Engineering School of Monastir, which is a nice city on the coast of Tunisia. My institution is ENIM, for École Nationale d'Ingénieurs de Monastir in French. And this school is attached to the University of Monastir. ENIM delivers about 250 degrees each year, and the duration of the study is 6 semesters. And I have to point out that all courses are taught in French in our school. Our school is also accredited EURES level. There are many research laboratories in our school. I am in charge of one of them called LEST, for Laboratoire d'études des systèmes thermiques énergétiques, which is created in 1999 Our laboratory was awarded twice the Presidential Award for the Best Research Laboratory in 2003 and 2020. Our laboratory includes 47 research professors, 3 technicians, and around 50 doctoral students and postdocs. Laboratory activities are centered essentially around 5 topics: aerothermodynamics, materials for energy, heterogeneous media, modeling and optimization of energy system, and finally, combustion. This picture is from our last scientific day organized last year. And we have many collaboration projects with French, German, and other universities, such as this collaboration with Rostock University, where we collaborate in the framework of Tunisian-German collaboration program Tuniger. And we organized this event titled Next Level Renewable Energy Technology in Tunisia last year. And you can found all the presentation of this event on our website. So in LIST, we have many research projects. One of them is what we are currently working on is the study of the interchangeability of hydrogen injection in gas pipelines with a special focus on the Tunisian context. The author are Mrs. Hazami Bidwi, PhD student, and my colleague, Dr. Hazem Tweti, and me. So let's start with this Tunisian context. This first chart gives an idea about the primary energy resources in the last 3 decades. One can observe that oil production have been going down since 2010, and the domestic production of natural gas in green plot has stagnated. I have to mention here that Tunisia receives royalties on the gas that is pumped through a pipeline running through Tunisia, connecting Algeria gas fields to Italy. According to the National Energy Observatory, the total final energy consumption reached in 2021 is about 9,700 kiloton equivalent, oil equivalent. And oil products accounted for around 53%. And followed by natural gas about 18%. Natural gas is consumed in Tunisia mainly in industry and residential sector. And this gas is essentially imported from Algeria with a percentage of 66%. This share represents a great handicap for the national energy balance, despite the recent entry into service of many other national fields, such as Nawara gas field. So the Algerian gas is mainly distributed in the north of Tunisia, and it is mixed with national gas and distributed in the south. The country of Tunisia has a large distribution network that covers most large cities and industrial area. State reports of 2020 indicates that the network infrastructure continues to grow, and the transport and distribution gas grid size reached 3,000 kilometers and 17,000 kilometers respectively. On the other hand, Tunisia may account on its huge renewable resource in photovoltaic and wind. There's resource. When we look to this map, we can appreciate the treasure that is available in Tunisia. When we evaluate this potential, we can see that Tunisia have a potential that is larger, greater than the mean value in the world. Solar potential and wind potential. Recently, Tunisia has set an ambitious renewable energy targets in its solar plant. This solar plant expects a share of 35% by 2030. And here we need further power flexibility measure to integrate these capacities. This can be done by converting electricity into hydrogen to increase the flexibility of power system. And also using this hydrogen or to inject this hydrogen in natural gas pipes, and this can be addresses many problems such as the large-scale application and the transmission problem associated with using hydrogen as energy source. Using grid, you can ensure transmission and distribution of hydrogen, and you can reduce the energy balance deficit of Tunisia. So this offers many advantages. I can mention here the ability to transport a large amount of energy with very little loss, decoupling supply and demand, and enhance sector coupling, enhance storage capacities, and offer the possibility of re-electrification. All this can ensure a successful and an efficient energy transition of our country. However, there are many challenges. I mention here the risk of leakage, the embrittlement of steel pipes and equipment, and the lack of and guidelines. For hydrogen blending requirement, I have to mention that hydrogen has the following characteristics: a significantly higher flame speed, less energy on volumetric basis, greater flammability and explosive range, and hydrogen burns at higher temperature than natural gas. So the addition of hydrogen can also affect the accuracy of metering, appliance materials integrity, and the operation of appliance equipment. An increased hydrogen concentration has the potential to result in undesirable combustion characteristics such as light back, higher NOx emission, the potential of uncontrolled reignition of unburned gas, remote from burner injector, and also the risk of HDs on appliance design. Sorry. So it is necessary to understand how adding hydrogen to natural gas might affect consumer appliance in order to determine if injecting hydrogen into distribution networks is feasible. Try to know how various pipe networks types affect the variation of in calorific value of natural gas after hydrogen mixing, and evaluate the proportion and quality requirements for hydrogen mixed gas in natural gas pipelines. When we speak about this, we need to define interchangeability. The interchangeability is the ability of a combustible gas to be replaced by another without requiring the adjustment of or other gas devices equipment, changing the mode of operation or changing the setting of such equipment. The units will continue to function safely and effectively. It is not new. The matters of interchangeability of combustible gases are not new. It was addressed by New in 1941 and 1943, where he established theory and practice of fuel consumption. It was addressed by Gilbert and Brink in 1956 in his publication issue of transition from synthetic gases to natural gas, and recently by Jones when he discussed mix of biogas, refinery gas, and liquefied natural gas with each other and air. Around the world, there are many demonstration projects in this direction. I can mention some of them. Hydroply in United Kingdom and other in United Kingdom, in Germany and in US. To study the interchangeability, we have to see the physical and chemical characteristic of natural gas. I mentioned here some of them: maximum higher heating value, minimum and maximum Webb index, maximum inertness, maximum carbon dioxide, maximum nitrogen, maximum and minimum specific gravity, and maximum and minimum gas density. And we have to look also to combustion parameters: methane number, the flame speed factor, the Sutting index. I have to mention here that the physical and the chemical characteristic of natural gas provide a range of gas composition, ensuring connected appliances operate safely. And the combustion parameters are used to specify a particular gas composition. When we look to previous study, we can identify that the adding of hydrogen to natural gas will alter gas composition, which in turn impacts the mentioned physical and combustion parameters. Two main parameters have to be discussed here. The first one is the higher heating value. It represents the energy content in a volume of gas when completely burned in air at standard conditions. It's a key to commercial action of the cost of natural gas as it refers to the energy value of the gas. A higher flow rate would be needed to achieve the same energy throughput with a lower, higher value gas composition. And the effectiveness of gas appliances like burns and cookers is impacted by low, higher heating value and low gas density. On the other hand, the other parameter, the second parameter, or the second main parameter is the Webb index. It measures the heat rate at the burner. This parameter is used to estimate the interchangeability of various gases, but it's still a global indicator. The performance of a burner should be the same for different gases with the same Webb index. And the Webb index is linked to higher heating value by this relation. Webb index is equal to higher heating value divided by square of mean gas density. This table shows some characteristic of methane and hydrogen. And hydrogen to natural gas, which has a high percentage of methane, we can see that hydrogen has a strong impact on combustion parameters such as density, higher heat value, and Webb index, because these combustion characteristics of hydrogen are lower than them of methane. To study, or for this study, we used gas tested. We used the Algerian gas as gas test. Here I give the mean composition of the natural gas from Algeria. And when we look to standards, we can classify natural gas in family, and then by group, and then by subgroup. Natural gas are in family 2. Methane gases are in group E. Same group has the same combustion characteristic and are clustered by the value of one of the interchangeability indicators: the Webb index, the superior calorific value or higher heating value, and the combustion potential. Here, we plot higher heating value versus different ratio of injected hydrogen in natural gas. We can see here that the higher heating value decreases linearly versus hydrogen injected. But when we look to Webb index, we can see that decrease until 80%.
It seems as if you're, at least I am quiet here. I don't know about my colleagues. Cannot hear you anymore.
We lost him.
Can you hear them, Alex?
No, I can't.
We cannot hear you, Professor Benchik. You're quiet.
Oh,
It's okay for me now?
Yes, thank
Okay.
you.
I have to switch this camera. Okay. It's okay for this slide? Do you hear me in this?
We can hear you. The slide is fine, but we don't have your video. Your black, so to say.
Ah, okay. So in this slide, I said that we will use in this study the mean composition of Algerian gas as a gas test. And this Algerian gas is characterized by a high percentage of methane. And when we look to standards, combustion gases are classified first by gas family and then by group of and subgroup. Natural gas are in family 2, where high methane gases are in group E. The same group has the same combustion characteristic and are clustered by the value of one of the interchangeability indicators, the Webb index, the superior calorific value or higher heating value, and the combustion potential. When we plot the higher heating value versus hydrogen percentage, one can observe that this higher heating value decreases linearly versus hydrogen percentage. And the Webb index decreases until 80% before climb back again. The main result here is that the Webb index varies between 43 and 52 megajoule per normal cubic meter. And also, it's still inside the range allowed by the group E reserved to high methane gas. The injection of hydrogen here doesn't change the gas group. And we have to mention here that equality of Webb index for different gas is necessary, but not sufficient condition for their full interchangeability. The Webb index is not longer the only interchangeability criterion. To improve the viability of the study, we must consider the combustion parameters. When we look to the combustion diagram here, and we start with this green point, the injection of hydrogen reduces the heat output, and the final operating point may remain in the region 5, dedicated to the steady and efficient gas combustion region, or move into region 1, where there are called the light back region, or move to the region number 3 for the yellow typing region, which is a soot region. And to perform a deep study of the impact of hydrogen on combustion parameter, we can use one of these advanced methods. In this work, we tested 3 methods, the one highlighted in red: Dayton criteria, the Lemberg method, and noise factor. In each method, specific parameters are evaluated. Let's start with the Dayton approach. This approach consists in simplifying the gas composition by converting the equivalent mixture of methane, propane, nitrogen, and hydrogen. All hydrocarbons are replaced with equivalent amount of methane and propane, and nitrogen is adjusted to preserve the Webb index of the original gas mixture. The second step was to calculate 3 interchangeability parameters, which are complete combustion indicator, flame lift index, and yellow typing or sooting index. The last step was to compare all these 3 parameters against suitable limiting values. For the first one, a complete combustion factor, which is defined by CO2 ratio in the substituent compared to the reference gas, and this ratio has been determined empirically by this equation. This method is used in UK, in Great Britain, and regulation in Great Britain stipulate that this indicator must be less than 0.48 to prevent incomplete gas combustion. The extreme value of this factor shall not exceed 1.49. As we can see in this plot, when we test different injection ratio of hydrogen, we reach the 0.48 after 7% of hydrogen injected in the natural gas. The second parameter is the lift index. It is an empirical parameter developed and used by Dayton to predict flame lift when the characteristic flame velocity becomes lower than the characteristic flow velocity. And this parameter is defined by this equation. When Li equals 0, there is no visible detachment of the flame. And when Li equals 6, this means the complete detachment of 50 to 100% of the flames. When we plot our results here, we can see that we can reach more than 35% of added hydrogen to Algerian gas, natural gas, without to reach Li equal 0. The third parameter was soot index. It allowed to evaluate the risk of transition from one type of gas to another in terms of danger. And it is given by this relationship. The gas safety regulation in United Kingdom requires that the limit of this index is 0.6. And as we can see in this plot, the addition of hydrogen into the mixture does not lead to sorting. Therefore, in terms of this index, natural gas and hydrogen mixture are interchangeable. So when you resume, we can see that for the first, only for the first one, there are a little limitation of hydrogen injection into natural gas. The second method is the Delbourg method. It's a French method for evaluating the gas interchangeability. And to ensure mainly the flammability condition of two gases, that the flammability condition of two gases are identical. So we need to evaluate what we call the combustion potential given by this equation. And this French method developed some reference gas, and these reference gas are given in this table and designed by G20, G21, G222, and G231. For this gas reference, there is specification for each one, and these specifications are given below. When we plot this reference in Webandex versus combustion potential plot, we can and delimit the region of this reference gas, and we integrate our results on this plot. We can see that when we add hydrogen to natural gas, we reach a limit of 20%. And after this limit, we are outside the diagram limit. So the maximum rate allowed by this technique was 20%, and to remain inside the interchangeability diagram. The third method tested here is the noise factor, which is given by this relation. And when we plot this factor versus hydrogen injected in gas natural, we can see that within a variation of less than 5% tolerated by this method, we can inject until 20% of hydrogen. So, according to this study, the natural gas and the natural gas enriched in hydrogen are interchangeable for well-defined proportion. A hydrogen content up to 20% is possible using the two last method 2 and method 3. A deeper analysis that considers the economic impact of this large-scale alternative must be performed. Also, studies on other national gas, Miskar, Nawara, are in progress. I have to mention here that the gas sector in Tunisia is governed by two main laws dated since 1999 and 1964. And the production of hydrogen as energy product is not covered by any existing provision under gas legislation. For any future development of green hydrogen activity, new regulation would have to be developed. Thank you for your attention. And finally, I would like to express our interest in clean hydrogen partnership, and we welcome all your suggestions and possible collaboration within this framework.
Yeah, Professor Benchik, thank you very much for this very nice presentation.
Yeah, sorry
well, you know, things happen, and but then after we figured it out that let's say I guess the battery of your headphone has been expired, so from that on it works out quite nicely. And thank you very much for this very interesting presentation about this update about the interchangeability of hydrogen injection in gas pipelines. This is also a topic which is very much discussed here in Germany. And let's say some of the local, let's say, gas provider or gas transportation companies, they claim that they can use 100% of hydrogen. So they are claim to be already hydrogen ready for the transportation. Others said, well, we just can use 10%, 20% or something like this. So this is also a very, let's say, very much ongoing discussion here in Germany, what we do see at the moment. And most likely, let's say we also will get some problems with the end user, because as you outlined, if the end user gets then a different gas quality and he has a sensible end use facility or end use apparat or end use system, then it might also get some challenge. So there's a lot of things which we still have to look at. Let's come back later to your presentation. There are already some topics popping up in the chat. And with this, thank you very much again for this very nice presentation. And I will now continue with our webinar tonight with the second presentation from Professor Dr. Alexander Alexev, as I said, from Munich University of Technology, as well as from Linde, and he will give us an update about advances in hydrogen liquefaction. So maybe Professor Benchik, you can close your screen, and then let's say we can have the presentation from Professor Alexev. Yes, so the floor is yours, and we are interested in your update.
Okay. I will go in presentation mode. I hope it works. No.
Yes.
Great. So many thanks, and Professor Kaltschmidt, for your invitation. I was last year. It was an interesting event for me, and I decided to participate this year again. Welcome to all. This presentation is about liquid hydrogen supply chain. Some slides are prepared by me, but some slides are prepared by colleagues of me, that is Chengguan Wu, Christian Wolf, Fabian Primke. They are PhD students or master students, and supervised by Professor Harald Klein and other supervisors, Sebastian Rehfeld from Technical University of Munich. Therefore, it's a kind of joint presentation, Linde and Technical University of Munich. The presentation consists of 3 parts. First, I would like to talk about hydrogen at the company Linde, technologies available, and one probably interesting slide about transportation, liquid hydrogen versus ammonia-based transportation route. Part 2, hydrogen liquefaction, liquefier setup, process design, specific power and capex. I will try to go bit faster for this part, because I think the part number 3, it's about liquid hydrogen distribution, is more interesting. I will tell you about some basic operations, and the Oliver, Christian, and Fabian do dynamic simulations. We'll talk about it and our first learning and recommendation. I have one slide about boil-off gas management. I'm not sure if you have enough time. If we have enough time, then I will present it. If not, I'll skip it. Yep, that's about Linde. Linde is a large industrial gas company. They are really great, 80,000 employees and representing 100 countries. Linde is a member of Dow Jones Sustainability Index, and we're proud of it. But I think more interesting is our hydrogen footprint, and the most important information: we are one of the biggest producer of hydrogen. We own and operate 150 plus hydrogen plants, producing more than 8,000 tons per day of hydrogen. That is unfortunately mainly gray or black hydrogen, but we are now going to be more greener and greener. We have already installed roughly 80 electrolyzers with a total capacity of 40 megawatt. This number is from 2021, I think. In 2022, we doubled our capacity, and I think in next years we will even increase the production of green hydrogen. What's interesting, we have a huge hydrogen pipeline. The total length is more than 1,000 kilometers, mainly in USA, in the Gulf Coast. But in Germany, in Leuna, close to Leipzig, we create a huge hydrogen pipeline works with compressor stations, and we have one cavern in USA, one of the biggest hydrogen caverns for storing. That is mainly for backup purposes in the USA. What we have some hydrogen liquefaction capacity. We have 5 huge plants in USA and 2 in Germany, and every day we produce 170 tons of liquid, and every day we distribute the 170 tons to our customers. So fill our trailers, drive trailers, and offload on the customer side. We are involved in a business with hydrogen refueling systems, stations for filling of hydrogen for mobility application. In terms of technology, we say our standard production technology is based on SMR or ITR. We can POX and electrolyzers, mainly PEM. We can carbon capture, post capture. There's like a mine wash, but pre-combustion, like oxy-fuel, that's we have in this portfolio. Liquefaction is that we have like a half of global capacity, and we manufacture storage, large tanks for storage of hydrogen, and trailers for transport of liquid and gas hydrogen. Good. The next slide, in principle, it is the same, therefore we can skip it. And that is a bit more information about the 2 technologies for transportation of hydrogen now. That's mainly by pipelines. As I said, in here in the upper part, and we use the pipelines and then caverns and the liquid. They are liquefiers shown. There are some trucks and cryogenic tanks and cylinders. And the numbers. What's interesting here probably that's Linde Engineering has a very interesting site. If you are interested in more information about hydrogen, then you can go for this link. One interesting technology, because it's related to the presentation before made by my colleagues, it is Linde has a technology to control the hydrogen extraction from hydrogen blended natural gas. If you inject the hydrogen into the natural gas, it's possible to remove the hydrogen from this mixture from natural gas. We use a special membrane technology based on the so-called high select membranes. And this link is you can look on this link, and then you may find more information for this special technology. I think that's interesting because it's linked to the pipeline transport. What's interesting information, Linde has, of course, the whole complete liquid hydrogen supply chain, but we are very familiar with the ammonia. As Linde owns proprietary ammonia production technology. If you need ammonia, as if you need a really mega size plant, you go to usually to Kellogg Brown Bowery, to ThyssenKrupp, or to hydrotopso. But if you need a medium-sized plant, it's still huge. It's still huge, but it's not so like mega science. That Linde, then in this case, Linde provides ammonia technology, and our customers are like Yara, and so they are very happy. This technology is interesting. They use not the air, but we use nitrogen for photosynthesis. They use air separation plant, separate air into nitrogen, oxygen, and only nitrogen goes into synthesis. That's looks more like to future green ammonia production plant based on the reactor using nitrogen and hydrogen. That's we are very familiar with this technology. Good. Now the slide is about because it's in the interesting discussions now worldwide how to transport hydrogen from one side to the other, and discussions are focused on two kind of technology. One technology is based on the hydrogen, liquid hydrogen. You produce the hydrogen, it's green or blue, you liquefy it, store on the export terminal site. Then you load the ships. Ships go to import terminal. In the import terminal, you can vaporize the hydrogen and put it into the pipeline grid, or you can use the liquid for further distribution. That's one sort of chain. And the second route, which is now under discussion, it's for ammonia production. You use the green or blue ammonia hydrogen for ammonia production, and you move the ammonia by ships. And on the import terminal, you need to convert the hydrogen, the ammonia back to hydrogen and put it into the pipeline grid. And there are a lot of studies about this comparison of these technologies, and they performed one internal study. It's because we are familiar with both technologies, with the ammonia and with the liquid hydrogen, and I'm not really willing to share all results, but one result is more about Tunisia. And for Tunisia, our study says that the liquid hydrogen route has a better economics than ammonia route. That's mainly because the distances or the distance is so relatively short, and for transport for the ship transport, they don't need so much fuel or hydrogen, and the boil of gas, the losses, they are really low, and therefore in our calculation, this LH2 transport is better if we are talking about Tunisia. Good, that was like a output of the study. Now I go to the hydrogen liquefaction. With some slides I presented already last year, therefore I will try to go a bit faster. That is a conventional setup of a typical hydrogen liquefier. If people are asking about hydrogen liquefaction, then that's usually they're talking about this hydrogen liquefaction unit. That is a device, you put the pressurized gaseous hydrogen from SMR, from electrolysis there, and that liquefies there. But the facility, the hydrogen liquefier facility is much more bigger. It's more than hydrogen liquefaction unit. You produce a liquid hydrogen, you need to store this hydrogen, usually in a spherical or horizontal cylindrical vessels. And then you transport this liquid usually by means of trailers, but you can use ships or other vehicles. And to manage the trailers, you need a filling base, special devices to fill the trailers. During the filling procedure or loading procedure, you have usually a replaced gas. You need to manage the boil of gas. One conventional device is a kind of recycle compressor. You can recycle your boil-off gas or replaced gas or flash gas back to hydrogen liquefaction unit. That's all required capex and opex. And one important part, usually the liquefaction unit, as of the conventional technology today, is use the liquid nitrogen for pre-cooling purposes. So you start with the ambient temperature, you cool first to liquid nitrogen temperature level, and then even further to 20 Kelvin. And then you need a liquid nitrogen. Then you have a kind of storage unit on site. You have to deliver liquid nitrogen by lean trailers, liquid nitrogen trailers, and you use this liquid for pre-cooling purposes. It evaporates inside of the unit and you produce the gaseous nitrogen. It's called waste gaseous nitrogen because it's not used, it's simply blown in the ambient. And that's the message. It's here that the hydrogen liquefaction facility is more than the hydrogen liquefaction unit. That's especially interesting to people asking for capex, and our people, as our sales manager, are struggling to answer this question because they need a kind of description. What is the scope? What do you need? Do you need a LH2 storage? Do you need a trailer and filling base? Do you need a recycling facility? Do you need a liquid nitrogen? That is all. Means usually capex and usually opex. That's only like if you're scheduling or if you plan to set up a facility is a more than hydrogen liquefaction unit. Good. This slide very known. It's thermodynamic properties relevant for liquefaction and storage and transport of hydrogen. What's here special? Yeah, you need a really cold temperatures. 20 Kelvin, this is minus 250 degree of C. Critical state is a 30 bar. That's important value because the liquefaction process, for liquefaction you need a supercritical hydrogen. You need to compress hydrogen before liquefaction, and over the critical pressure, and critical is 30. It means for liquefaction you need a 50 or 20, better 25 or 30. Evaporation heat is very low, like 1 kilojoule per mole. And what is special in hydrogen, if you liquefy hydrogen, during the cooling of the hydrogen goes through a kind of conversion. It's a conversion from a normal composition ortho to para. During this conversion, some additional heat is generated. It's in the same order of magnitude like evaporation heat. It's 1 kilojoule per mole. And that is an additional heat you need to remove during the liquefaction mode. You cool it, and you need to convert this, and then that is that value which is considerably high, comparable with evaporation heat. Density and liquid condition is just a 70 gram per liter. It's very light liquid. Good. There are some slides explaining this ortho-para conversion, but I will skip it. That's interesting slide is the temperature enthalpy diagram. It shows the difference. If you take a hydrogen, that's like a normal hydrogen, that's a red line, and you cool it from ambient temperature, then you will liquefy it. That's this red line. But in reality, you need this conversion from ortho to para. In real line is like a black one, and it's you need a really 1 kilojoule more of heat to remove. That's interesting. The minimum liquefaction power required for liquefying of hydrogen in a reversible process. It's really reversible process is like a 3.9 kilowatt hours per kilogram. That's 10 times more in comparison to LNG, to liquid natural gas. Liquid natural gas is 0.3 and here's 3.9. The good message is that this liquefaction power depends on the pressure. The value of 3.1 is given for pressureless hydrogen at ambient pressure. But what the good is that all conventional hydrogen manufacturing technology, for example, steam methane reformer, produce the hydrogen at the elevated pressure at roughly 20 bar. And the minimum liquefaction power required for this feed, as for elevated pressure hydrogen feed, is lower. It is adjusted 2.87, 25 bars, 2.8. That's a 25% less than it's required. I said that there's a minimum liquefaction power required in a reversible process. In a real process, you have a losses. The process is not reversible, and the typical efficiency is like a 30-35%. At the end, it results in a real liquefaction power of 10 or 12 kilowatt hour per kilogram. Good. That how the hydrogen liquefaction work. Please focus on this picture on the right side. You take the hydrogen feed, it's dry, purified hydrogen, supercritical, like a 20-25 bar, and you simply cool it by means of an external cooling process. You cool it. You need this ortho-para conversion tool. Therefore, via some catalyst filled in the heat exchanger here, you cool and convert, and then you achieve the temperature of roughly 30 Kelvin, 30 or 25 Kelvin, and you expanded this hydrogen. And after is enthalpic expansion, the liquid, the feed is liquefied. Then you have your para hydrogen. That's in principle very simple. In detail, if you look on the process, it's maybe more complicated, but the basic principle is very simple. Just cooling, can convert it, and then expand. That's all. This cooling process, normally in all liquefier, is done in its two-step cooling approach. Usually you cool first to the liquid nitrogen temperature level at 80 Kelvin in the first step, and then goes in the second step to the temperature level of 20-25 Kelvin. Why? It's because the liquid nitrogen temperature level, it's relatively simply achievable. Liquid nitrogen, you can use a conventional cooling technology. That's really like a commodity, well understandable, and it's not problem at all to achieve the 80 Kelvin. And this way, using the more or less standardized conventional cooling technology to go to 80 Kelvin. The challenging part is really to go from 80 to 20 Kelvin. That's like if you go to Mount Everest, then you go from 0 level to, I don't know, level 5,000, 6,000 kilometers or 4,000 kilometers. Every person can go to this level. That is if you go from 300 to 80. But the last, if you go from 4,000 to 8,000, that is really difficult, and that is here. That's like you go to basic camp, and then from basic camp to the summit. That's really difficult. And the temperature entropy diagram, the process shown, you take a 20 bar hydrogen, you cool it, and you cool it, and you cool it, you achieve this liquid nitrogen temperature. That's the basic camp, and then you go further to 20-30 Kelvin, then you expand the liquid hydrogen, and then it's liquid. The next picture shows the same diagram, just low part of them below 120 Kelvin. That's you go from 80 Kelvin and to 30 and then expand. That's all. And that's again that the zoom of the lowest part. If you pre-cool the hydrogen, liquid hydrogen to temperature of 36 Kelvin, expand roughly half of this hydrogen fate is liquefied. That's not good because you cooled and then only half of them is converted into liquid. It's better cool it to temperature of 30 Kelvin, if expanded, and then roughly 75% liquefied. But the best idea to cool it as cool as possible to 22, 23 Kelvin. And then you expand your hydrogen, then it's liquefied almost completely. Good. And that is an example of a real process. I think our liquefier in Germany is based on this process. As I said, the hydrogen feed, dry, purified, supercritical 2025 bar is cooled first in the first heat exchanger to liquid nitrogen temperature level to roughly 80 Kelvin. Use the liquid nitrogen from a vessel in contact current heat exchanger. You evaporate the hydrogen, liquid nitrogen, and you cool this feed. And then you're starting this last cooling from 80 to 20. It goes through, I think that 1, 2, 3, 4, 5 heat exchangers, and then achieve the level of 25, 20 Kelvin, expanded, and then you are liquefied. And for cooling of the hydrogen in this heat exchanger, the cold stream is used. That is here. This cold stream hydrogen. It's produced by expansion of hydrogen in the expanders. You know, if you expand gas in expanders, it's cold, and it expanded one expander and then expanded into next expander, it becomes cold, and you provide this cold stream for the heat exchanger and call the feed stream. And in principle, you need to compress this expanded stream again, but that's very cold temperature. They have not any compressors able to compress it here at this temperature. Therefore, they warm up this part compressed in the heat exchanger and cold it again to 80 Kelvin. And then when the gas that goes for the expanders becomes cold, and this cold gas is used for cooling of the fed gas. Yeah, that the terminologically, from thermodynamic point of view, that it's external hydrogen clot process that consists of Joule-Thomson process, reverse Brayton process. So this cooling cycle is operated with normal hydrogen. There are no any ortho-power conversion here. Only feed is converted here. Used to 2 compressors, 3 expanders. It's liquid nitrogen pre-cooling. Integrated ortho-power conversion here in this heat exchanger and the smaller heat exchanger. And what's nice in this process that the hydrogen feed pressure is more or less free parameter. You can use a 20, 25, 30 bar and 60. And this process, the integrated clot process, has their own pressure levels. That's like a technology used today in hydrogen liquefaction. The different companies, different suppliers are using different schemes, different flow sheets, but the basic process is quite the same. What's new? Probably, yeah, I said the conventional technology is using liquid nitrogen from external source for external cooling process for the first stage. That's okay for today's liquefier. Today liquefiers have a capacity of less than 40 tons per day or 50 tons per day, and power is required is less than 20 megawatt. And the amount of liquid nitrogen required here is not so much. It's in terms of moles, it's comparable with the hydrogen feed. So the amount is to cool that it's comparable with liquid nitrogen. in terms of moles, as norm cubic meters. In terms of mass, it's a factor of 50, like this, because nitrogen is simply has a molecular weight 28 and hydrogen just 2. But in the future, if the larger hydrogen liquefiers will be built, I think all companies are now claim that they will are able to deliver 50 or 100 tons per day, or 200 tons per day, 300 tons per day. I discussed. Then in this case, this amount of liquid nitrogen is a bit higher, and probably it's not good. The existing liquid nitrogen infrastructure is not able to deliver this amount. We need to implement a kind of special nitrogen cycle. It may be a nitrogen-based reverse Brayton-Clot technology used today in ASU. That's I think kind of option for and in the further future, in 20 years, if the really huge hydrogen liquefiers will be installed to capacity 500 tons per day. But I have here number 300, but really 500,000 tons per day, 1,000 tons per day is capacity higher than 100 megawatt. Then we can use a year for the pre-cooling purposes, mixed fluid-based process like it's used now in the LNG technology. It is developed for huge amounts. It's applicable here. In terms of cost, it's even cost-efficient technology. That's like a roadmap for the next 2 decades. For the final cooling stage, the processes based on the Brayton-Clot processes will be still the preferred processes. There are some options available. What working fluid we can use? That's the helium, that's the hydrogen, neon, or mixtures of all these fluids. Number of expanders need to be optimized, 2, 3, or even more. And what's interesting options, I think all people are thinking about this. It's a using of Joule-Thomson expander here instead of the expansion valve. If the hydrogen amount becomes higher, then it makes sense to introduce the expander. That's a probably new slide. I think Linda has communicated very often. This slide on the left side was published in 2011 about the energy specific power demand for liquefaction of hydrogen. And in 2011, we had already a system in Leuna with like a 10 kilowatt hours per kilogram. And the expectation was that we can achieve 7.4, 6.4 if we scale up our system. But in the development was not, if you compare with the real development, these numbers were not achieved. It's not because not achievable, but the market demand was not so. It was different. The market expectation was not market demand was not for a very efficient system. The market demand was more for low cost system, and the development was focused on the reducing of the cost, not the specific power. And like if you look on the corrected approach, as it's now it's expectation from today, then this value 10 or 9 kilowatt hours is already achieved. That's no problem. The expectation is we can go to 8 kilowatt hours per kilogram or 7 kilowatt hours per kilogram in the near future. Okay. If you look on the specific capex, then that's very known effects, economy of scale. If you double the capacity, then the specific cost reduced by 33% roughly. That's works for hydrogen liquefaction too. The one problem is here, this economy of scale works well for heat exchangers and expanders, but that's really the scalable devices, but compressors are still a challenging issue, and we need a compressors, high capacity for hydrogen, that's still a problem. Good. The idea was to go to liquid hydrogen distribution next slide, but I'm now out of time. It's Professor Cashman.
Yeah, well, sorry for being unpolite. First of all, thank you very, very much for this very nice presentation and about this excursus into, let's say, thermodynamics. This is what I most like in my studies, you know. So from that point of view, I'm, let's say, back to the roots, so to say.
Yeah.
Thank you. Thanks a lot for that. And thank you very much for this, let's say, update about, let's say, liquefaction. And sorry for being unpolite, but let's say we already have 8:10, and
it's okay for me.
Yeah, we are slowly running out of time, but I understood that, let's say, you are willing to provide, let's say, a copy of your slides, and that, let's say, who all the people interested in your presentation can have a closer look. So maybe Professor Benchik can, let's say, also come up, and maybe you can close your screen, Professor Alexev, because then we have a little bit more, let's say, space. Yeah. So thank you very much. So we are close to an end, and now the question is, let's say, how do you see it in the years to come when it goes to, let's say, hydrogen transportation? We have seen, sorry, that on one hand side, let's say, Alex showed that, let's say, we can transport also on the short distance, let's say, hydrogen as a liquid, which is quite demanding from energy point of view. And you, Maher, have shown that, let's say, we also can transport it via pipelines, and there also as a, let's say, feed-in gas to the existing natural gas. So where do you see the borders of the different technologies? I mean, I guess we will not transport, let's say, a mixture between natural gas and hydrogen. Maybe we do, I don't know, from Tunisia to Europe. And maybe it's not the very best solution to transport the liquid hydrogen just around the corner, yeah, to regasify it. So therefore, where do you see your, let's say, borders or the most promising application areas for the different technologies? Maybe we start with you, Alex, that you give an idea about, let's say, the liquid areas, and then maybe you, Maher, about the markets, what you see for, let's say, pipeline transport, and maybe also combined transportation with natural gas.
I think that this combined transportation is a crazy idea. Probably it works, but that's, I think, difficult to guarantee the composition. And the pipeline, it's not a simple pipeline. The pipeline works. It's a difficult structure with the T-pieces, and so I think if you put the hydrogen, it's a challenging to guarantee the whole composition and the whole pipeline. I think that's the main issue. Maybe it works. At Linde, for example, we are supplying a kind of technology for removal of hydrogen from so mixing pipelines. But I think it's challenging, but that's a cool idea. Generally, in terms of cost, the transportation of hydrogen by means of pipeline is the best. It's really, in terms of cost, the costs are minimized, and if you have a hydrogen pipeline, that's the best. We use the hydrogen pipelines for transport of hydrogen to customers, and are happy. But I think the economy of hydrogen pipelines, you cannot build the hydrogen pipelines with a 5-inch diameter. That doesn't work. You need a really like a 40-inch or 30-inch of huge pipeline, and that the problem is if the amounts of hydrogen to be transported are relatively low, and invest a lot of capex in such a huge, heavy hydrogen pipelines, then the economy doesn't work. The hydrogen pipelines require huge amount of huge flow rates, and that's I think a kind of issue. The pipelines are very in terms of economic, it's a good solution, but the assumption is that you have a huge amounts in flow rates. That's for me kind of issue. And if you have this amounts, then the hydrogen pipeline works well. But we have still not so, the production of hydrogen is still not so really high, and that will grow next years. But it's still for a hydrogen pipeline. I think that it's still we need to check the numbers. But my feeling is the flow rates are still too low for hydrogen pipelines, and therefore we are looking on the other technologies like liquid hydrogen, like ammonia, because that's like a niche for these amounts which are now available.
Okay. Thank you. So thank you very much, Alex. Maher, where do you see the possibilities and the markets for such a combined transportation in the existing natural gas grid, especially on the background that, let's say, when you would like to sell this mixture, then also the end-use facilities and the end-use, let's say, usage has to be adapted to the mixture.
Okay, thank you. I agree with Professor Alexander, because when we use existing infrastructure of grid gas, we can reduce cost. So the advantage of injecting hydrogen in pipeline gas is the use of existing infrastructure. And when we look to the map of infrastructure of gas in Europe or here, in North Africa, it's very developed. So through a little modification, through a little precaution, we can use this infrastructure. And I have to remember that there are Transmed pipeline between Algeria and Europe, and this can help the transportation of a huge amount of hydrogen through this gas pipeline. For our country, I think also that the conversion of hydrogen and this integration of hydrogen, green hydrogen, into other processes may be develop what we call the added value to this product. When we when we convert hydrogen to ammonia or methanol or other product, we can develop local markets here. We can add some value to this hydrogen, and but the cost of transportation will be, as said by Professor Alexander, more costly.
Yes, thank you very much for that. I mean, the point is indeed, I mean, if you would like to use the existing infrastructure, then last week we have seen that, let's say, the test concept goes to the way to provide, let's say, methane out of hydrogen. That they produce basically methane, try to recycle at least part of the CO2, and then go to methane, and then you can use the overall infrastructure. Then it's very easy. And I learned also from Professor Alexev, or from Alex, that let's say we have 10% only of the energy demand when you would like to transport this in a liquid status. Is this an option for, let's say, Tunisia, that you go for the hydrogen derivative and then go for methane? And maybe also to you, Alex, do you see this as a valid option compared to hydrogen? How do you see this from your point of view? So maybe we start with Maher and then go to Alex.
When we using hydrogen to produce methane, it's a solution also. But we need to investigate some investments, some development technology for CO2 capture from cement industry, for example. So it is not an easy it is not easy for to capture this CO2 and to develop this process. I think it's more easy to develop other hydrogen derivatives than the use of the product of methanol. For the development of methane, yeah, and inject it in gas pipeline and to produce CO2. It's problematic, I think.
Okay, Alex. When you switch on the micro, we can also hear you.
Thank you.
Sorry. It's true, huh? I'm even not joking, you know.
Yeah, I think that in principle, if you look I think that the techno-economics, it's the right word. You have really to look on the capex and opex, and I think in the last 10 years we were really the whole scientific community. We had some expectation that we can reduce the cost for production of synthetic methane as a synthetic natural gas, but they are still relatively high, and they are not on this level which are targeted 10 years ago. Now the community looks on derivatives like ammonia, like methanol, and yeah, that's for methanol and ammonia. What's good? The transportation costs are relatively low because you can use the existing infrastructure, tankers, ships, and existing terminals, ports. But the conversion is still the cost for conversion the hydrogen to ammonia are relatively high, and it may works if you have a really cheap hydrogen, low cost hydrogen, and if you have a cost efficient ammonia plant, methanol plant, then it can happen that then you will produce the kind of energy carrier ammonia, methanol, which is competitive in Central Europe. Now the cost for the power are relatively high because natural gas costs are high, and then our energy costs are high, and then maybe it works in several cases, but you really needed to start with a low power cost. I think we need electricity as a electrical power in the range of 30 or 20 euros per megawatt hour. Then probably if you convert half of this energy, then you have a 40, and then if you transport it, you have a 50, and then you can sell it in Germany for 70, 80, make a profit. And that may work. So that's now our hope, while people are investigating ammonia option and liquid hydrogen option. That's
well, we will see how the development is ongoing, and I think we can, let's say, leave it as it is with our discussion, because I mean, let's say, future will see how the development will go, and how cheap we can provide the electricity, and how flexible the systems are to, let's say, squeeze in or feed in hydrogen on one hand side, or to develop, let's say, completely new energy systems or provision chains. Was this, let's say, maybe I will, let's say, come to maybe the very last question, and maybe please a short answer, 1 or maximum 2 sentences. Where do you see the, let's say, pipeline transport of hydrogen in Tunisia in 10 years' time, and where you see the liquid hydrogen transportation on a global scale in 10 years' time? So maybe we start with Maher and then go to Alexev, or to Alexander, sorry, to Alex.
Okay, thank you. I think my talk today was put the focus on injection of hydrogen in gas pipeline in the Tunisian context. We have a deficit in our energy balance, so we have to seek for solution to reduce this deficit. We have a great potential of renewable energy, so we can develop this solution of producing hydrogen to be injected in the local infrastructure to reduce the importation of natural gas from our neighbors' country, and to be independent from these resources that's such as gas natural.
Okay, thank you very much, Alex. Where do you see the liquid hydrogen transport in the next 10 years?
I think in the next 10 years, we will have our results of our study shows that the transport, if you have a distance lower than 2,000 nautical miles, then the liquid hydrogen transport may be sufficient. If we are talking about amounts of 100 tons, 200, 300 tons per day, that's feasible. I believe that in 10 years, we will have a transport of liquid hydrogen in this amount, but for the liquid hydrogen market, not for gasification, but for mobility application, they need a liquid hydrogen. And if we may produce low-cost liquid hydrogen in low-cost power countries, then it may work. For the pipeline transport, we need a really huge amounts of hydrogen. And if the industry will be able to generate hydrogen amounts in order of magnitude comparable with the natural gas, or like a 20% or 30% of natural gas amounts, then the transport by pipelines becomes very attractive options.
Okay, then thank you very much. And with this, I think we can now finalize or terminate or close our session for tonight. First of all, I would like to thank first Professor Maher Bench-Hihik. It's still not perfect, but I'm working on this. Yeah. Thank you very much for your outstanding presentation about the interchangeability of hydrogen injection in gas pipelines. And then I would like to thank Professor Alexander Alexev from Munich University of Technology and from Linde about his wrap-up or update about advances in hydrogen liquefaction. And with this excursus into thermodynamics, thank you very much, both of you, for that. And before I terminate, I just would like to mention and would like to thank, first of all, of course, the translator for doing the duty to translate our, at least my bad German English, into good French. Yeah, thank you very much for that, Faisal. And of course, I would like to thank also Fabian Karels, Felix Mendler, and Shoki Aslush for supporting this webinar in the background. And last but not least, of course, GIZ for sponsoring the translation. With this, I just would like to mention next week, same time, same place, same time. We have another interesting topic, or for me, one of the most important topics, because the certification and market establishment for hydrogen. So we will get a report about the development of, let's say, a hydrogen market at the European Energy Exchange. So there is currently starting an activity to figure out how are the prices, how is the price development and the price formation at the European Energy Exchange for hydrogen. So this is quite interesting. And this is also something which is quite new. And then we will have a second presentation about hydrogen guarantee of origin, because if you don't have the claim that it's green, or then you will not get any support, and you cannot get any tax reduction or CO2 tax reduction. And then I think it's even worse from the economics, as let's say Alex just explained you a couple of minutes ago. So from that point of view, it stays interesting. And on the further course of our webinar, we also will have a hydrogen, let's say, country report from New Zealand, from the US. We will have one from Jordan and from Egypt. We will have one from Nigeria and from South Africa. And of course, we also will have other topics in the next 3 to 4 weeks. And therefore, you are warm welcome to come back to our webinar next week, same place, same time. With this, thank you very much, everybody. I wish you a beautiful evening. Don't work too hard. Enjoy the evening and see you next week. Bye-bye.